Hi everybody, and welcome back to the continuation of example 1. We started this back on page 57 and now we're continuing with parts B and C on page 58. Now just so we don't have to keep flipping pages back and forth, I went ahead and recopied the definitions of the two transformations T and U. Okay, and part B would now like us to calculate the matrix of the transformation UT, the composition. Okay, now this part of the problem would like us to do this directly. Okay, using the same technique that we did in part A. Directly means we're gonna start with our basis alpha, just substitute in those two vectors. Remember, alpha was the standard ordered basis for R2. So we will take 1, 0, and 0, 1 and substitute those two in. Okay, well, by definition, ut is just the composition of u and t, so we could rewrite this as u of t of 1, 0. And t of 1, 0 we actually calculated back in part A. What we got was 1 plus x. So this is u of 1 plus x. Okay, you can look back at part A and check me on that. And then similarly, ut of 0, 1 would be u of t of 0, 1. And in part A, we calculated t of 0, 1 to be 1 minus x plus x squared. Okay, so to finish this, we need to do two calculations here, starting with u of 1 plus x. Okay, and looking at our definition of u, the 1 plus x is the p of x that we're seeing up there. Okay, so we kind of played this game back in part A. To calculate u of 1 plus x, we first noticed that the first coordinate of our 4 tuple is going to be 0. Let me be consistent with my colors here. Okay, so that's going to be 0. Actually, it's going to be 0 down here too, so why don't we go ahead and fill that in. And then what we need to do to finish our calculation is to find these three numbers. Okay, so let's go down here and do that. So p of x at the moment is 1 plus x. Okay, its first and second derivative would be 1 and then 0. And we need to substitute in 0 for all of our x's. So p of 0 would be 1 plus 0 is 1. P prime of 0 is going to stay 1, and p double prime of 0 is going to be 0. So it looks like we're going to get a 1, and a 0 there. Okay, and then let's see, for this p of x, 1 minus x plus x squared, its derivative is going to be minus 1 plus 2x, and then the second derivative is going to be 2. Okay, if we substitute 0 in for all of our x's there, we'll get, let's see, 1 minus 0 plus 0 squared is 1. Negative 1 plus 2 times 0 is negative 1. And then finally, p double prime of 0 is going to stay 2. Okay, so we're going to get a 1, negative 1, and a 2 out of that. Okay, and as we said before, because of the fact that we're using the standard ordered basis on R4, we can look at these vectors and they're going to become our columns directly in our matrix. So the matrix of, not T, UT, okay, going from alpha to gamma coordinate should be, first column is going to be 0, 1, 1, 0, and the second column is going to be 0, 1, negative 1, 2. Okay. And so that appears to be our answer for part B. Okay, now what about part C here? Well, it's interesting because they're asking us to do exactly the same thing that we did in part B, to calculate the matrix of UT, but to do it in a different way. Okay, we used a direct method in part B. Now what they'd like us to do is to use theorem 2.11. Okay, what does that mean? Well, theorem 2.11 says this, that if we want a matrix for UT, we can get it by taking the product of the matrices for U and T separately. Okay, I'm just literally recopying what theorem 2.11 says here. And the thing about it is, we calculated these two matrices in part A. I'm going to go ahead and just copy those down. Okay, so the matrix for U back from part A looked like this. 0, 0, 1, 0, 0, 0, 0, 2. Okay, and then the matrix for T looked like this. 1, 1, 0, and 1, negative 1, 1. All right. And so next thing we would do is to just multiply these matrices together. Let's do a couple of the entries together. So in the upper left-hand corner, we'd be taking the dot product of this vector times this vector. But for that, because we've got all zeros in the first row of the matrix for U, we're just going to get a 0 in the upper left-hand corner here. Okay, next thing we do is to take 1, 0, 0 and multiply that by 1, 1, 0. That's going to give us a 1. Okay, if you take that dot product. Let's do one more entry together. If you take 0, 1, 0 times this, that's also going to give you 1. And notice, if you look at these three entries that we've just calculated so far, they agree exactly with those three entries up here. And if you kept doing this, completed this multiplication, I'll let you check this part, you'll discover that we end up with exactly the same matrix that we got in part B. And we should, because we're calculating the same matrix. So by using Theorem 2.11, we have just confirmed our answer to part B. Okay, and we're done.